Hello. With this class, we finish Module 2, Types of Movements. We are going to apply some of the things we have studied to a practical case. Let's remember that the kinematic study of the movement is in charge of obtaining the geometry of the movement. That is to say, it studies the movement of the object without taking into account the causes that originate it. Recall that we have seen that the parabolic shot with the choice of axis that we have on screen is the composition of two motions, a uniform rectilinear motion on the x-axis and a uniformly accelerated rectilinear motion on the y-axis. We have already seen the equations of these types of motions, and they are the ones that appear on the screen. The composition of the acceleration, velocity, and position of each of these movements will give us these quantities. And with them, we have perfectly characterized from the kinematic point of view the motion of the object. We are going to calculate these magnitudes. To a practical case, Jota is in one of his basketball training sessions, and Amanda tells him that the modulus of the speed with which he has thrown the ball is 8.47 meters per second, and the angle of inclination with respect to the horizontal is 50 degrees. The basket is 3 meters from the ground, and 6.21 meters from Jota. At the moment of launching the ball is 2 meters from the ground. We are asked for acceleration vector, velocity vector, position vector. We are asked to draw the trajectory of the ball. We are asked for the maximum height that the ball reaches, and we are asked if the ball will reach the basket. We are going to calculate all the quantities in the international system. Well, the first thing we have to calculate is the acceleration vector, and for this we have to establish our reference system. We place the reference system in Jota and on the ground. With this reference frame, the movement of the ball will take place in the xy plane, and therefore, with the choice of axis we have made, A sub x will be 0, since on the x-axis the motion is rectilinear and uniform, and A sub y will be minus 9.8. Therefore, the acceleration vector will be minus 9.8 Jota in meters per second squared. The vectors shown in red are the acceleration vectors at different points along the trajectory we think the ball will take, although we will calculate it later. We are now going to calculate the velocity vector. To do this, the first thing we have to do is to calculate the components of the velocity. On the x-axis, the velocity, the x component of the velocity will be v sub 0 by the cosine of alpha, since it is the adjoining leg of angle alpha. Since the motion is uniform, the x component of the velocity will be 5.44 I meters per second. On the y-axis, we have uniformly accelerated motion, and we have an initial velocity. The initial velocity will be v sub 0 by the sine of alpha. Taking into account the equation of a uniformly accelerated rectilinear motion, we see that v sub y will be, in this case, v sub 0 sine of alpha minus g times t. Substituting values, we obtain the y component of the velocity. The velocity vector will be the vector sum of these vectors. If we want to find these components at different instants, we will give values to the time, and thus we will obtain each of the components. Recall that in the first module we saw that the velocity vector is a tangent vector to the trajectory at all times, and therefore the velocity will be the one that has appeared there. Let us analyze this velocity vector and its components at different instants. At the initial instant, we have component x and component y, both positive. At the instant 0.66 seconds, the x component is non-zero, equal to 5.44, while the y component is 0. Recall that we saw that the y component condition of the zero velocity implied maximum height as shown on the screen. Later, we will check that this is so. And at instant 1.14 seconds, we see that we have x component of the velocity and y component of the velocity, one being positive and the other negative. If we observe the x component of the velocity, we see that it has a constant value in the different instants that we have calculated. And if we calculate it in all, we would also obtain it. And this agrees with the fact that in this axis, the movement is rectilinear and uniform, and therefore the x component of the velocity is constant. The y component of the velocity varies its value, being positive, null, and negative. Therefore, it is a uniformly accelerated rectilinear motion, as we have already seen. Let's see now the position vector. In the x-axis, the motion is rectilinear and uniform, and therefore the position on that axis will be given by this expression. With the choice of axis we have made, x sub 0 is 0. If we substitute values, we obtain that x is equal to 5.44 t in meters. On the y-axis is a uniformly accelerated rectilinear motion, and therefore the equation that governs this motion on the y-axis in terms of position is the one we have on the screen at the moment. Initially, the ball is in the hands of J, who is 2 meters above the ground. Therefore, substituting values of y sub 0, v sub 0 y, and g divided by 2, we obtain these values. Finally, the position vector will be the vector sum of these two components. Now we want to calculate the trajectory of the ball. To do this, what we have to do is to give values to the time, as shown in the attached table, and now we will plot these values over time. Indeed, the trajectory of the ball is a parabolic trajectory. Next, we are asked the maximum height of the ball. To calculate the maximum height, we saw that the condition was that the y component of the velocity, since x is constant, must be 0. From this expression, we calculate the time, obtain 0.66 seconds, and substitute in the expression of the position along the y-axis. Substituting this time value, we obtain that the maximum height is 4.15 meters. In the table, we see that effectively in 0.66 seconds, the height is 4.15 meters, which is the maximum height, and the position along the x-axis is 3.6 meters. We are also asked to calculate if the ball reaches the basket. What we need to know are the coordinates of the basket. These, from the problem statement, are x equals 6.21 and y equals 3. Therefore, the ball has to occupy that position at the same instant. How do we do it? Well, in the expression of x equals 5.44 t, we replace the x by 6.21, we clear the time, and we obtain that this is 1.14 seconds. With this time, we go to the expression of y. We substitute the time for the value we have obtained. And if the ball reaches the basket, the y must give us precisely 3, which is what we obtain. From the values that we had found before in the table, we see that for t equal to 1.14 seconds, effectively, the x is 6.21 meters, and the y is 3 meters. Then the ball arrives at the basket. Let's recall what we have done throughout this class. We have studied the parabolic shot, which is the composition of two motions. a uniformly rectilinear motion on a horizontal axis, which in our case was x, and a uniformly accelerated rectilinear motion on a vertical axis, which in our case was y. We have calculated the maximum height condition. We have calculated the maximum height. The maximum height condition is v sub I equal to 0. And finally, we have seen if the ball arrives at a point of coordinates a, b. How do we solve this? It is imposed that x has to be equal to a and y equal to b, but these values have to be reached at the same instant. Well, that's all.